In an earlier video, I made these Makita battery-powered lights, but they had a few fatal flaws. They drew power even when turned off, causing the battery to slowly drain. And worse, there was no low voltage protection, which could potentially kill some batteries. So today, we're going to fix those problems while building a DeWalt version with a more powerful LED and a noctua fan attachment. We'll try out some American-made PCTG filament, and we'll build a MagSafe style tool attachment system. Let's look at exactly what went wrong with the original design. I put this switch here, which works to turn off the light, but it leaves this DC booster connected, which still uses power, even when the light is off. That's called quiescent current. Thanks to the commenter pointed this out. The fix is simple enough. We just move the switch to before any components on the negative side. Now the battery won't drain when turned off. Another commenter pointed out that these batteries don't necessarily have low voltage protection. If a battery is drained too low, it can be permanently damaged. Fortunately, I found these low battery protection circuits designed specifically for 18 to 20 volt battery systems, and they only cost about $2. If the voltage drops too low, it will automatically disconnect. One thing my Makita design was missing was any way to rotate the attachments. I couldn't find a satisfying way to 3D print rotating attachments. But while playing with these magnetic connectors for another project, I had an idea. What if we use these round magnets to build a MagSafe style system to connect accessories to so we can rotate around the magnet? These magnets are powerful enough to hold a tool head in place, and I can add little dimples to add a satisfying notch. They can also support up to 10 amps, and we won't be going anywhere near 10 amps. I wanted a more powerful light, so I found this 40 watt 18 volt cob LED. Simply giving it battery voltage will cause it to quickly burn out. The cob LED has a metal backplate where we can attach some heat sinks, but even that's not enough. Cob LEDs like this require a constant current driver. I found this tiny module that will limit the total power of the cob to less than 1 amp, which should keep it from getting too hot. For the fan, I'll be using this Noctua 120mm 12 volt PWM fan. Any PC fan would work, but the yellow and brown combination tempted me. I wanted to see what it would look like an inverse UPS truck or something. These fans have 4 wires, 12 volt, ground, tack, and PWM, which is used to control the fan speed. This version of the fan won't be adjustable, so we can simply unsolder those 2 wires, and without them, it'll always run at 100%. To get the battery voltage down to 12 volts for the fan, I'm trying out these new step-down converters I found. They are so tiny. If you missed the Makita video, the key to making these work is these battery attachments that you can find on AliExpress for only a few dollars. They make them for all the major tool brands. The yellow of this one is just a little bit off, and that bothers me, so I kind of wish I'd gone with black. Now it's time to design everything in Fusion. It's a bit ugly, but it'll have to do for version 1. The adapter is attached with embedded M3 square nuts. The magnets live in these little housings, which I designed to be separate pieces, so I could build many tools without having to redesign the attachment point. So let's get printing. This is 3D Fuel's PCTG Pro in Toolbox Yellow, and it prints relatively easy with the settings that they provide. There were some more surface blemishes compared to what I'm used to, and a bit more stringing, and it also clings to the printer bed way harder. It was actually really hard to remove it from the textured build plate. 3D Fuel has a bunch of interesting filaments, all made in America, and I'm excited to try a few of those out in future videos. Before we can assemble this, there's one huge issue with the magnetic battery plan. This exposed magnet would be connected directly to battery voltage. This means just touching it could potentially shock you with up to 20 to 40 amps at 20 volts. Ouch. Not only that, but shorting it could damage the battery or even cause fires. I began to research how other magnetic connectors work, and they mostly use sense pins, which is a low voltage connection. Once that connection is verified good, the chip sends the full power. The problem is that the connectors I bought only have a positive and negative, no sense wires. After a lot of researching, I found this tiny little IC called the MP5056 that is designed just for this purpose. This tiny 3x5mm chip packs a ton of features. It has a voltage range up to 36 volts, which is twice what we need. And you can configure it just by attaching resistors and capacitors, no microcontroller needed. This chip will completely stop power flow if it detects a short, and it will delay power on until it knows it has a good connection. The only problem is, I couldn't find any ready-made module with this chip on it, or any similar chips. Which means it's time to design my own PCB. I learned how to make PCBs from watching YouTube videos, and I made a bunch of them over the years. If you've never done it before, it may seem intimidating, but I promise it's not that hard to learn. All we need is some free software called KiCad, and it's one of the best open source tools I've ever used. You basically just place the chip on the schematic editor and connect all the lines. The datasheet for the chip tells you exactly what to do, and even gives you a sample layout. Most of the pins are just voltage input or output, labeled VIN or VOUT. The enable pin turns the chip on and requires between 1.8 and 6.5 volts. We can get that voltage with something called a voltage divider from the 20 volt input. With 2 resistors in series, the line between them will be divided according to this formula. 20 volts with a 100K and a 22K resistor is 3.6 volts. Perfect. I connected the auto pin to a test point, but left it floating. In this configuration, it'll constantly try to get a good power connection over and over again. If I'd grounded that pin, you'd have to turn it off and back on every time it had a little flicker. Capacitor on the timer pin will set the delay for hot plug insertion and fault reset. The next crucial pin is the current limit pin, called ISET. The datasheet gives us a formula we can use to figure out what resistor to use to limit the current. I'll never use anything more than 2 amps, so I figured 4 amps is a good limit with some headroom. For that, we need a 30K resistor. We then attach a capacitor to the soft start pin, which lets it turn on over about 20 milliseconds. I chose a 220 nanofarad here because that's what the datasheet used. The IMON pin is used for current monitoring. We're not using it, but the datasheet recommends connecting it to ground through a 10K resistor. The power good and fault pins can be used to show some status, but since I'm not using them, I routed them to test points and left them unconnected. The FB pin is a voltage pin that we can set to enable the power good signal. Anything above the given voltage is considered good. We don't need this in my design since we're not using the power good pin, but I hooked it up to a voltage divider exactly the same way I did the enable pin, just in case I want to use it in the future. PD just ties the voltage out, which will let the capacitors discharge after powering them. Then I opened the PCB editor and drew this layout. Power flows through under the chip and then out all these pins on the top. These extra capacitors smooth out power and are recommended in the datasheet. These things on the right here are unidirectional TVS diodes. They prevent the voltage from going back in the wrong way. So like if you applied a voltage through here, it would not damage the chip or the battery or anything. And all that's left to do is order the PCBs. And that's where today's first ever channel sponsor comes in, NextPCB. They make it super easy to get PCBs by providing a KiCad plugin. You can literally add it to your cart right from inside a KiCad. Or you can just drag and drop your Gerbers right on their website. They show you a preview with a ton of options. I went with the black solder mask and left all the options at their defaults. After I placed my order, they quickly made them and they arrived in about a week. The quality was top notch, especially the stencil, which came in a metal frame. Right now you can get your first order PCBs made for only 1 penny. Thanks to NextPCB for sponsoring this video. Now NextPCB could also assemble the PCBs for me, but I kind of like to do that part myself, at least in low quantities. It also gives me the opportunity to test out different components if something doesn't work or my calculations were off. Let me show you how easy it is to build one. First, you put the chip down on a flat surface. A lot of people use tape and some other spare PCBs to hold it in place, but I'm only doing a few, so I don't bother. Next, you line up the stencil and put this totally not toothpaste on here. This is called solder paste, and it's made of microscopic balls of solder suspended in flux. When it heats up, those balls melt into liquid metal and then become solid. So you just drag across the stencil with a plastic scraper. Remove the stencil and it's ready for components. I ordered the MP5056 chips from DigiKey, and for the rest of the parts, I used this handy sample book that came with thousands of components. These components come in different sizes ranging from small to ridiculously small, but I went with 0805, which is just big enough that you don't need a microscope, even though I'm going to use one in the video so you can see what I'm doing. As you're placing the components, you don't have to get it exactly right, because they'll magically fall into place when we heat it. Once that's done, I place it on this tiny little USB-C hot plate. This thing only costs about $20 and works surprisingly well. I've had this one for a few years now with no complaints. After a minute or so, we can see the solder begin to melt and the components are pulled into place. After letting it cool, you've got a beautiful, professional looking PCB. Now it's time to test it out. Well, crap. My first ever sponsored video and the PCB I made that's supposed to protect me from shocking myself and destroying my battery did exactly the opposite. There's 2 really important lessons here. First, at a minimum, check your assembled board with a multimeter, and better yet, test your circuit using a current limited power supply, rather than going YOLO and hooking it up directly to battery voltage that could output up to 40 amps. Second, pay attention and don't put the unidirectional TVS diodes on backwards. They have a tiny little line on them, and that shows you which direction they go. If you do it backwards, it has the opposite effect and acts as a direct shunt from input to output, which is kablamo. And not the cool kind of kablamo. Anyway, after reversing the TVS diodes and checking all the voltages with a multimeter on a current limited power supply, I tried again. This time we get a nice 18 volts. If I short it using a screwdriver, it goes dead. Perfect. This is exactly what we want. Now we can safely lick the magnetic connector. Actually, don't do that. Let's just put this together. To hold these pieces in place, I'm trying out a new glue, which is cured in seconds with a UV flashlight. I'm impressed. It works great. Inside the tool handle, the 18-volt battery protection module is wired to the Hot Swap module. I made them both the same size so they can fit in the handle, and it's secured with some double-sided tape. To harvest the fan, I just snipped it off and cut away all this little plastic, revealing an 11mm little brass pin. This can be glued inside the housing. quick side note, K&F Concept sent me this little vacuum and duster to try out, and I have to say, this is one of those things I didn't know I needed before I had it. If you want to support the channel, an affiliate link is in the description. And there you have it, a nice cool breeze for my Noctua DeWalt fan. I don't have air conditioning. I don't know if this is the most practical use of these magnetic connectors, but I think it's pretty cool and I can't wait to try this in some future projects. Anyway, I'm working on like 4 other videos right now, so if you're interested in content like this, I think YouTube has some sort of feature to like track when people post or something. Anyway, thanks for watching.